Hello, welcome back. This is lesson 3 from unit 6 of our AP Calculus course. This unit is all about more applications of derivative. We're looking at some really real-world applications, things about physics, economics, maximization, minimization, stuff like that. So I hope you're having as much fun as I am. Let's get right into lesson 3. Example 3.1. A particle moves along the x-axis so that its position is given by s of t equals t cubed minus 5t squared plus 12t for 0 less than or equal to t less than or equal to 4. We're going to use the Canid's test to find the minimum velocity of the particle and the time at which it occurs. So we want to find the minimum velocity. Well, let's get right to it then. To find velocity, we need the derivative of position. Remember, velocity is the rate of change of position. So 3t squared minus 10t plus 12. But we want to find the minimum velocity, so we need the derivative of velocity, which you could think of as acceleration. But I usually say v prime when I'm taking a derivative to find out something about v. If I'm taking a derivative to find out something about the acceleration, then I usually call it acceleration. But it's up to you. All right, well, we can see that v prime of t is equal to 0 at 10 over 6, or 5/3. So that's our only critical number on this interval from 0 to 4. So to use the Canid's test, we need to show each one of these. Well, we could use a table of values. That's one way to show the Canid's test. So t of 0, t of 5/3, and we have t of 4. And then this is v of t. Velocity at 0 is 12. Velocity at 5/3, just going to simply plug that into a calculator, if you don't mind. We are using a lot of calculators in this unit. So in my class, we prefer the TI-89, but we can use Desmos Online right now if that helps. So we'll go right here. Now, of course, you wouldn't expect to be able to use an internet-based application on the actual AP exam, but this will be okay for us. The important thing to remember is that you need to be able to take a numeric derivative. You need to be able to take a numeric integration, and you need to be able to find a intersection point between two curves or the zeros graphically. Those are the things that every calculus student has to be able to do with a calculator. All right. Looks like 3 2/3. I'll just say 3.667. All right, and we can plug in 4 pretty easily. I think 16 times 3 is 48, minus 40 is 8, plus 12 is 20. So the minimum velocity, and it doesn't look like they gave us any units, so I won't give them any units back. Minimum velocity is 3.667, and it occurs at t equals 5/3. Okay, now we're going to solve the same problem using what I call a modified first derivative test. Now, the first derivative test is about finding local mins and local maxes, but here I am talking about an absolute max and absolute min. Well, there's a special kind of case where you can use something like the first derivative test, but it requires that we only have one critical number or in some way be able to logic out what is the true absolute max of the function. So let's go ahead and see how that would work. Well, we already did the first part. Remember, we got that velocity was 3t squared minus 10t plus 12. And we got v prime of t to equal 0 at 5/3. So if we put that on a number line, now remember the AP graders do not grade your number line, okay? Well, there's 0, and then here's 4. But what they grade are your sentences, and the number lines kind of help you form those sentences. So here's 5/3 right here. Well, our derivative, since our derivative was 6t minus 10, Our derivative was negative here. If you plug in the number 1 for t, you'll get 6 minus 10 is a negative 4. So negative. And then over here it's positive. So we also found a couple of different things. This is the only critical number on this interval. So we know that for the entire time in this interval, the velocity decreases until 5/3 and then increases afterwards. So we're going to say that t equals 5/3 is the only critical number. And that's important because if you had two different places where the derivative went from negative to positive, which one was further negative before it started going positive? I don't know. You see, it would be a lot more difficult. So it helps that we know that there's only one place. So 5/3 is the only critical number of v of t. And v prime of t changes from negative to positive there. So t equals 5/3 must locate a relative minimum of v of t. And then v of 5/3 we said was 3.667. So those are two different ways that we can find minimum values. And which one we use kind of depends on the situation. If possible, I much prefer to use the candidates test. But the candidates test requires us to be continuous on a closed interval. And if we're not continuous on a closed interval, then we can't use it. But if we can be, boy, I'd rather use the candidates test. Okay. Let's use the candidates test to find the absolute maximum velocity. All right, we can do that. Well, the candidate, I'm just going to use a little bit of computer-aided cheating here, and I'm going to copy and paste this. All right. Well, we already knew that t equals 5/3 is the only critical number. And we're testing the endpoints. So t equals 5/3 is a critical number of v. So we can conclude that 20 is the max of v, and it occurs at t equals 4. Very easy to use a candidate test. Why is the first derivative test not useful in finding the absolute max? Well, the question is, did it, we can look at this and say, well, if it went down more from 0 to 5/3 than it did from 5/3 to 4, then clearly 4 is bigger than 0. But just because 0 to 5/3 is a smaller interval than 5/3 to 4, that doesn't prove anything. Sometimes graphs can go down steeply, sometimes they go down more gradually. So it's not useful because we don't have that information. So I'm just going to say we do not know if v of 0 or v of 4 is greater. We don't know. We know they're both greater than 5/3, but we don't know which one is bigger than the other. All right, let's take a look at this problem. Gottfried has a special dog named Isaac who can do calculus. While walking along a rectangular pool, Gottfried throws a stick into the water to a point 45 feet forward and 20 feet out as shown in the diagram. Isaac can run at 30 feet per second and swim at 15 feet per second. How far down the edge of the pool should Isaac run before diving in to minimize the time required for him to get the stick? All right, so they're walking along a pool. And then all of a sudden, Gottfried's going to throw this stick right here. Okay? And that distance that he throws it is 45 feet down this way and 20 feet out this way. Now, the dog is going to, we would think the dog would just jump in and swim towards it. But dogs can do calculus, you see. And that's why they'll run a little way Now, this is definitely the shortest distance, right? The hypotenuse is the shorter. It's longer than these two legs, but it's definitely shorter than them combined. But since the dog can run faster than he can swim, he's going to run a little way and then at the absolute perfect moment switch to swimming. Let's figure out where that dog will jump in, because that dog can do calculus and will minimize this distance. I'm going to call this distance here x. So I'm going to be using a right triangle, and that's really the secret to this problem. Let x, whether we're trying to figure out how far down the dog runs or what, make sure that you let x be the defined length of the triangle. So this length here has to be the square root of 20 squared plus x squared from the Pythagorean theorem. And since distance is equal to rate times time, the time that the dog swims is equal to the distance the dog swims divided by the rate. So we're going to call big T of x the time it takes the dog to fetch the stick. It's going to be the distance the dog swims, which we agree is 400 plus x squared over how fast does the dog swim? 15 feet per second. Plus, well, now if this is the length, x is the length that we had in this triangle. That's the length that he didn't run. So 45 minus x is the length that the dog did run. And that's divisible by 30. We're going to use a calculator to find when the derivative of this function is equal to 0. So when you're using a calculator to solve a problem on the AP Calculus exam, you'll need to show what the derivative is if you had to do something like graph it to find where it was 0. If you just need to find the derivative at a specific value, you can just say t prime of 7 equals and put the number, because you're allowed to do a numeric derivative. But the 89 will actually take the derivative and give it to you, so you can let it do that for you, or you can figure out the derivative on your own, which I'll do here. The derivative of this is 1/2, and the half times 1 over 15 because we 1 over 30. And then this will be 400 plus x squared to the negative 1/2 times the chain of 2x. Then plus the derivative of this term is simply just a negative 1 over 30. Now let's graph this on our Desmos. So I'll call it t prime of x is equal to 1, well, I don't need to put the 1, right? 400 plus x squared to the negative 1/2 times 2x all over 30 minus 1 over 30. The function of t is not defined. I guess it just wants f of x. Oh, because I'm saying f prime. That's okay. Let's say t of x. Okay. All right. Now we can see it's a very flat line, and we're oftentimes very interested just at what's happening at the x-axis. So it makes sense sometimes for us to change our settings to where our y scale is really small. And then we can focus on where that 0 is, and it will show us that it's at 11.547. So 11.547 is the length of x. How far down the edge of the pool should Isaac run? We're going to run 45 minus that. That will minimize the amount of time. All right. Got a problem somewhat similar to that. I'd like you to pause the video now and give it a try. All right, let's see how you did. A swimmer is 2 miles in the ocean and wishes to get to town 3 miles down the coast, which is very rocky. The swimmer needs to swim to the shore and the walk along, and then walk along shore. He can swim at 2 miles per hour and walk at 4 miles per hour. To what point should he swim along the shoreline so that the time it takes to get to the town is a minimum? So this here, we're going to say x. We're going to let that be x. So this will be 3 minus x. And so this will be the square root of 4 plus x squared. So the total time as a function of x is going to be the square root of 4 plus x squared, the time swimming, divided by 2 miles per hour. And then plus 3 minus x, what we have left to walk, divided by 4 miles per hour. And let's take the derivative. This is 4 plus x squared to the 1/2, so this will end up being 1/4 times 4 plus x squared to the negative 1/2 times the chain rule of 2x plus the derivative of 3 minus x is a negative 1/4. So we'll just go right back into decimals and we'll type that right back in. So that is 4 plus x squared to the negative 1/2 times 2x over 4 minus 1/4. And we can see our solution is at 1.155. So x equals 1.155. And in this problem, it's that's the point that he should swim down. So 1.15 miles down shore is how far he should swim. All right, let's find the dimensions of a 12-ounce can that can be constructed with the least amount of metal. So we're given the formula for volume and we're given the formula for the area. So we know that it has to be a 12-ounce can, and just note 12 ounces is 244 cubic centimeters. So that's going to be our volume. 244 cubic centimeters is equal to pi r squared h. Now I need to solve this so that I can plug it into my area function and minimize it, and I don't want to have r's and h's, so I need to get rid of one of them. Well, I'd rather not have square roots, so let's take 244 and divide it by pi r squared. Now that I know what h is, I can plug that in for h. And there we go. Well, we could do some simplifying here. It's 2 pi r squared plus the pi's cancel. We're still going to have an r down here, and this will be 488. You know what I realized? We did not justify on our previous problems. I forgot to do that. And now I'm upset that I'm in the middle of a problem and realizing it. So we're going to go back and learn how to justify those. Anyway, sorry about that. Okay, so let's take a look at this one. We have area is equal to that. Let's find area prime. For pi is just a constant, r, minus 488 over r squared. And let's graph it. Notice you would love to be able to do the candidates test, but I can't do the candidates test on this. And the reason why is that the r value of 0 is not allowed because of the division. And there's no limit on how big r could be, because the bigger r could be, the smaller h ends up being. So this is bounded. There is no closed interval that we can set up where it's continuous. So this is a prime is equal to 4 pi x minus 488 over x squared. All right. So it seems to be 3.386. Now, it's kind of difficult to see what's happening here since we are going to justify this one. You know, it's so vertical. What's happening? Well, let's go and take a look at our settings and see if we can't make the y values bigger. So I'm going to keep the x values from 3 to 4. And, well, I think now you can see it, can't you? We can see that this is going from a negative to a positive. And that's what we're going to say. We're going to say that just like we did earlier when we talked about, we're going to say R equals 3.386 is the only critical number of A, and A prime is less than 0 on this interval from 0 to 3.386, and A prime is greater than 0 on the interval from 3.386 to infinity. So R equals 3.386 minimizes A. And we want to find the dimension, so we've got one of them. To get the other one, we simply have to plug it into this formula and find out what it is. You can type that in if you want. It's 244 over pi 3.386 squared. All right, so I'm kind of giving away how we can justify there. Let's go back and look at these problems here, since we forgot to justify. The justification that you use here, there's a couple ways you can do that. You could argue that it makes no sense for the dog to run backwards, so you could actually use the candidates test and say that x cannot be bigger than 45. If this x was bigger than 45, the dog ran backwards. And you could also say that x can't be less than 0 because it makes no sense for the dog to run past the stick. But I'm going to assume that, I don't know, maybe he can just swim extra fast if he goes to the left, and we'll just stick with using the the first derivative test, the adjusted first derivative test, and we'll simply say the exact same thing. We'll say that x equals 11.547 is the only critical number, and t prime is less than 0 from 0 to less than t less than 11.547, and t prime is greater than 0 for, that's supposed to be x, not a t, for 11.547 less than x. So we can see that it goes from negative to positive, and so that must be locating a minimum. And then we went down all the way to it, and we went up all the way after it. And we would say the same thing on this one. We would say that t prime is less than 0 for, I'll use intervals here, for x on 0 to 1.155, and t prime of x is greater than 0. And we saw that in the graph. It went from below to above for 1.155 to infinity. So x equals 1.155 must locate a minimum of t. All right, that's it for this lesson. Until I see you again, take care.